Pleasure to introduce speaker Dr. Luis López Velazquez from Universidad de Zaragoza, Swiss. Is associate professor in this university. He authorship more than 40 publications in matrix orthogonal polynomials, orthogonal polynomials on the unit circle, and parorthogonal polynomials in the unit circle. He is the father of the CMB, knows a very, very important success from the paper published in 2003, Linear Algebra and Applications, which received 166 citations according to Maths.net. The title is 5 Diagonal Matrices and Zeros of Orthogonal Polynomials on the Unit Circle. And he was the starting point for a very fruitful theory. His first article about the topic of the talk of this lecture appears in Communication on Pure and Applied Mathematics in 2010, and this joint work with Maria Jose Cantero, Leandro Moral, and Alberto Grunbaum is said to be orthogonal polynomials and quantum walks, Schur connections. And in this talk, Luis meets orthogonal polynomials, harmonic analysis, operator theory, and random walks, as well as their quantum version. A pleasure to introduce Luis, and I hope we will enjoy with this nice lecture. Let's go, Luis.
Thank you very much to the nice chairman for his brilliant introduction, and also to the organizer for trusting on me for this talk. I hope you will enjoy it. I don't know if you will learn too much, but I hope at least you will enjoy it. You can see many colors in my picture, in my presentation, have a meaning. You have to put attention on that. For instance, you have there something like orange and green. And also with the authors, this is a fruit of a joint work along many years, and will tell you some results that I have obtained with different teams of people. And the interdisciplinary character of this talk is maybe shown by the kind of people that is involved. Mathematician, applied mathematician, pure mathematician, mathematician with a physical flavor, physicist, quantum physicist. In green, you can see the people with more oriented to physics, and in orange, people which are more oriented to mathematics. But I know that this is an artificial separation, but at least to understand that it has many people with different orientation have been involved, and this is behind the success of all the results here. And indeed, this is the message from the full talk, that joining people and effort from different orientation gives to you something good, for sure. Let's start, and we will play between math and physics, and you will see clearly when. We will start with math. As you have seen in my title, Schur functions are the cornerstone of everything that I'm going to talk about. First, you have to know what is a Schur function. Schur function is nothing else but an analytic map on the analytic map of the open unit disk. And they have a very nice characterization by a sequence of parameters that appear when we apply certain kind of algorithm, which is called the Schur algorithm, that produces a new Schur function starting with a previous one. So in general, we can generate a sequence of Schur functions starting from a given one. And this Schur function are called the iterates of the original one. And in this iteration, we had to evaluate the Schur function at the origin, and the evaluation, these complex numbers, which have modulus less or equal to 1, are called the Schur parameters. Indeed, it can happen that this sequence terminates. In general, the sequence has modulus less than 1, and once we get one of them with modulus equal to 1, then the sequence terminates, because the last function is a constant function, a constant unimodular function. We have here an example of this kind of terminating situations. But generally speaking, you will get infinitely many Schur functions and Schur parameters. It happens that they give this parameter give a characterization of each Schur function. So there is a one-to-one correspondence there. So we will use this notation to understand that given the parameters is decide which kind of Schur function do you have that determines the Schur function. Of course, each iterates is like starting with a Schur algorithm a number of steps afterwards. So the end Schur iterate has a sequence of parameters which comes from a truncation of the original one. These things can be a little bit more complicated. So important are these Schur functions, scalar Schur functions, are the matrix valued one. Have values on matrices with norm less than 1. They are called matrix Schur function. And if you think that they are only a non-interesting generalization, you are in a mistake, because they are even more important than the scalar Schur function. They are the analytic map on linear list which values in contraction, because they can be defined for matrices or even for operators. They can be operator related. In any case, they appear in many fields. I summarize here some of them, both in mathematics and physics in application. And I will talk about one of these applications. First of all, let's understand the role of Schur function in the theory of orthogonal polynomials. We will deal with the two paradigmatic cases corresponding to having an orthogonalization of the power of Z, or the orthogonalization of the positive and negative power of Z. We will talk about orthogonal polynomials and Laurent orthogonal polynomials. The first one are typically used in the case of a measure on the real line. The orthogonalization of this power give a sequence of orthogonal polynomials in the real line, and they are characterized, as you know very well, by a three-term recurrent relation, which is codified by a Jacobi matrix. On the other hand, Laurent orthogonal polynomials are the kind of orthogonal polynomial which you use in the case of the unit circle for different reasons. When you have a measure on the unit circle, the orthogonalization of this positive and negative powers give rise to a sequence of Laurent orthogonal polynomials on the unit circle. And the first clue that tells you that this is the right choice is the fact that this kind of orthogonal polynomials satisfy a 5-10 recurrent relation. Then I circle the role of the 3-10 recurrent relation for the real line. And it's codified by a so-called CMV matrix, which is a unitary matrix depending on certain parameters, which are the parameters of the recurrent relation for the orthogonal polynomials on the unit circle. These parameters have modulus less than 1. And of course, you know perfectly that the central problem in the theory of orthogonal polynomials is to find relation between measures and the corresponding parameters of the recurrent relation. Of Schur functions. Schur functions appear in relation with orthogonal polynomials on the unit circle. It's not difficult to understand that, because they are functions that are defined inside the unit circle. They are analytic functions on the unit circle, in the interior of the unit circle. If you take a measure, you can produce, as I told you, a sequence of orthogonal Laurent polynomials on the unit circle, and they are characterized by a ZMV matrix, which depends on certain parameters. On the other hand, you can define the so-called Stiegler's function of this measure on the unit circle, and then a simple transformation like this gives to you a Schur function. Those who know about Schur function in this setting typically don't introduce it in this way. They introduce via a relative of the Stiegler function, which is the so-called Carattori function, and then a simple mode transformation gives to you the Schur function. But this is equivalent to that presentation, and indeed, I will do in that way. You will understand in few pages. And there is a miracle is that the Schur function, the parameters, the Schur parameters that characterize the Schur function are the same parameter appearing in the recurrent relation for the orthogonal polynomials. This is the so-called unanimous theorem. They appear in connection with the theory of orthogonal polynomials and the unit circle from the very beginning, but only the beginning of the 20th century, when the Schur function acquired a very important role in this theory, because Issai Schur developed in a couple of papers many deep results about orthogonal polynomials on the unit circle, not previously known, and all the story has to do with the fact that many problems about these orthogonal polynomials can be translated into problems of analytical functions via Schur functions. And the cornerstone of this theory, developed by Issai Schur, is a relation, what we could call a Schur relation between orthogonal polynomials, measures, and parameters that has this form. What he found is that the Schur function of this modified measure factorizes product of iterate and what he called inverse iterates, because they are Schur functions characterized by the rest of the parameters, but in inverse order. What nowadays is known as KHRUSHCHEV formula. You think that this is not a formula, but a relation, we can write it as a formula. But in any case, why is it so important? It originates a classification of orthogonal polynomials on the unit circle, which is based on the asymptotics of these modified measures. Just one example to understand the implication of this kind of result. For instance, we can study when these modified measures are convergent. I will not talk about the kind of convergent here. Let's say weak convergent, but we can discuss afterwards if you want about that. And of course, this translates into a problem of the convergence of a sequence of analytical functions. And due to the fact that they have a direct connection with the Schur parameter, you can translate this convergence into a characterization in terms of the asymptotic behavior of the Schur parameters. Don't pay attention to the right side, which is a little bit complicated, but it allows you to translate an asymptotic problem about measures into an asymptotic problem about functions, and this gives to you in the end a characterization in terms of the parameters of the recurrent relation. Questions that appear in this setting. Results appear first on the real line, and then we try to translate them to the unit circle, but this is not always like that. And this is one instance where this is not like that, because Schur functions appear for the first time in connection with orthogonal polynomials on the unit circle. And then a question arises: what is a Schur function for orthogonal polynomials on the real line? Do we want to translate all KHRUSHCHEV theory to the real line if possible? First, we have to understand which kind of function we are expecting as Schur function for the real line. If we think on the unit circle, the Schur function are the analytical self-map of the interior of the unit circle. Of course, if we are working with a measure on the real line, we should expect something like this: analytical self-maps of something, for instance, like the upper half plane, complex plane. This is what is called an Evalina function. This is what we should expect as a real line version of a Schur function. And what is the Schur algorithm for the Evalina functions? There are, in the literature, you can find a different kind of real line version of the Schur algorithm, but they are much more complicated than the standard Schur algorithm. They have the uses. I will not use them. I will propose another one. And what about KHRUSHCHEV formula for orthogonal polynomials in the real line? This should be quite far, because we don't know even what a Schur function for orthogonal polynomials in the real line should be. This will tell you if you have found a real line counterpart of a Schur function, because if you don't have a nice KHRUSHCHEV formula for the real line, I don't think that you can say that you have found a real line counterpart of the Schur function. What kind of KHRUSHCHEV formula we can expect? Remember, this was a KHRUSHCHEV formula for the unit circle, a factorization. What happened on the real line? What can we expect? Something like that? Of course, product of Schur functions are again Schur functions, but product of Nevalina functions are not anymore Nevalina function. Instead, we should expect a sum. A sum of Nevalina function is again a Nevalina function. What about matrix valued version of this? Should be quite hard because even for the unit circle, this was not given by the standard methods given the KHRUSHCHEV formula. Physical setting. Let's talk a little bit about something that can be considered mathematics, random walks, and also physics, like quantum walks. And I will present both situations in parallel, as I did with the real line and the unit circle, because indeed they are in correspondence with these two situations. Random walks. Random walks is a system in which you have a countable set of states, and they evolve via a stochastic matrix, which gives to you the probability of passing from one state to another one in one step. Of course, if you allow for several steps, then what you have to do is to make the power of the stochastic matrix and then to take the corresponding coefficient. The typical example is the Bequeathed process, which is given by a stochastic metric which is tridiagonal, and this paves the way to the use of orthogonal polynomials on the real line in the study of random walks. About quantum walks, I cannot explain here why, but the states of this kind of quantum system are the unit vectors of a Hilbert space. Evolution is given by a unitary operator because this operator preserves the norm of these unit vectors. What's the evolution law? It's like this. If you want to, every unit vector is a state. So you can ask for the probability of passing from one state to another one in one step. Then you apply the unitary operator to your initial state, and then you make the inner product with the rival state. And this is a complex number. This cannot be a probability. What's happening is that the modulus square of this complex number gives to you the probability of this transition in one step. You have to take the power of the corresponding unitary matrix. These complex quantities, which are not probabilities, but whose modulus square is a probability, they are called amplitudes in general. They are complex numbers. The typical example here is the so-called coin walk, which reflects a situation that happened in the labs. When you deflect a system of electrons, we can have a spin up or spin down through a magnetic field. They evolve in different, they separate in different beams. And this is what happened here with this kind of quantum walk, is that depending on the spin, at each side you have two possibilities of your spin, and then you evolve to the right or to the left depending on your spin. This is like a simplification of the deflection of a beam of electron by a magnetic field. The unitary metric behind this kind of system is a ZMB matrix, and this paves the way for the use of orthogonal polynomials and the unit circle in the study of quantum walks. Let's talk about something which is quite well known in the case of random walks: recurrence, the study of return properties. Let us fix, let's label our states 0, 1, 2. Let's talk about the return properties of one state, like its state 0. What's the probability of returning to the state in a step? I mean, you start at that state and you want to know the probability of returning to the same state after n steps. Of course, it's the power that you have here in the screen. And with these quantities, you can get a generating function, which we call the return generating function. Even you can make the sum there because it's a geometric series. And but if you ask for the return probability, no matter when, I mean, what is the probability of returning to the state 0, but independent of the time? At some moment, what is the probability of eventually return to the state 0? This is a sum like this, in which summand is the probability of returning to that state, but for the first time in n steps. These quantities Rn are not the previous one. If we sum the previous one, we do an overcounting. How do we get these other quantities? Smart trick by introducing in between any two factors here a projection like that kills the possibility of returning to the state 0. Then what we get is really the probability of returning to the state 0, but for the first time, because we are avoiding with this projection the possibility of returning in an intermediate step. And we can obtain, we can use these quantities to build a generating function again, but we call the first return function. Of course, evaluating at 1 this function, we get the return probability that we want. And we will not use this one, but this other one that makes the same work for statistical reasons. We can sum this. Again, it's a geometric series, and we can make the sum there. And if you ask about the relation between these two generating functions, there is a nice and simple relation, which is called the Runewald equation. Maybe some of you remember that this relation appeared before. Imagine that S is the Stiglitz function of a measure on the inner circle. Then F should be the Schur function, the corresponding Schur function. So if S were the Stiglitz function of a measure on the inner circle, F would be a Schur function, but that's not the case. So this opens several questions concerning random and quantum walks. First of all, there are any Runewald equation for quantum walks. That means that we should understand what is recurrence for quantum walks. But why to ask this? Because quantum walks are related to unitary operators. Unitary operators are related to spectral measures that lie where the spectrum is on the unit circle, and then maybe Schur functions appear codifying return properties for quantum walks. So the second question is, if there is a Runewald equation for quantum walks, do Schur functions have any connection with recurrence? And what in that case, what are the consequences of KHRUSHCHEV formula? Consequences, I mean. And what about if we return not to another state, but a subset or subspace of states? How to describe this situation? And finally, do we have, if we can answer positively all these questions, do we have any payoff? That's it. I mean, do we have any mathematical payoff for any eventual use of Schur function in describing recurrence in quantum walks? Try to answer this question. And at the same time, we will answer the question related to orthogonal polynomials on the real line and Schur function. So let's cross the math to physics bridge. After that, we will do the opposite. Let's describe what recurrence is for quantum walks. We can translate the formalism that we had for random walks to the case of quantum walks. And the generating function that you have here are just the translation of the generating function that you had in the case of random walks, a return function and a first return function. But there is a difference. The coefficients, the Taylor coefficient of this generating function are no more probabilities, but they are amplitudes. So you want to get a probability, you have to take the modulus square of any of these coefficients. So only the modulus square of the coefficients of this of the Taylor expansion that you have there, of this generating function, have the meaning of a probability. And what is Q here? Q is the analog of the projection that avoided to pass through the initial state. So this should be here, the orthogonal projection onto the orthogonal, to the state that you want to avoid. You want to return to that state, but for the first time, for this you had to avoid to pass through this state at intermediate steps, and you use this kind of projection. Surprisingly, you have a Runewald equation which is exactly the same one. Why? Because it's a purely algebraic property. It's not so unexpected in the end. And so does it mean that Schur function appear here? Take into account that a unitary operator gives to any vector on your Hilbert space, gives a measure, which is called a spectral measure, which is supported on the spectrum of the operator. And using this spectral measure, you can see that the function that you have here is nothing else but the Stieltjes function of these measures on the inner circle. So f, the f that you have here, the first return function, is indeed a Schur function of the spectral measure of your state, the state whose return properties you are studying. What happens if you study the return to a subspace? Then your scalar Schur function becomes a matrix or operator valued Schur function as you want. And so matrix Schur function come into play. We have discovered a quantum walk interpretation of Schur function. They codify, they are the generating function for the return property of a state. And we have here an expression for the such Schur function depending on the unitary operator that address the evolution and on the state of whose return properties we are going to study. Now we cannot evaluate f at 1 and expect to get a probability. If we evaluate f at 1, we make the sum of complex coefficients. We need to make something different. And it's not difficult to understand due to Parseval theorem that the right thing to make the sum of the modulus square of all the coefficients of this generating function, which is the return probability, is just taking this integral here. This gives the return probability. And if you want to get the expected return time, you have to make a kind of different integral with your Schur function. So, and this has very deep and unexpected results, which contrast very much with the case of random walks. First of all, the expected return time is related with the winding number of your Schur function, and this is an integral. This was not true for the case of random walks. You can find simply in a very, very simple system with a non-integer expected return time. And when is finite expected return time, it's possible to see that it depends only on the fact that state should be a combination of finitely many eigenvectors of your unitary operator. And the expected return time, indeed, is the number of eigenvectors involved in the decomposition of your state. And this has a strong consequence that for every finite dimensional quantum walk, expected return time is always finite. This was not true in the random walk setting. And what about KHRUSHCHEV formula? Does it have any meaning? Talk about quantum walks. One, we know a Schur function appears as a K tool to study recurrence for quantum walks. What's the meaning of KHRUSHCHEV formula? And it's something like this. Imagine that you have a quantum walk and you can split your Hilbert space in two pieces, the green part and the blue part, in two pieces that have an overlapping, which is the red part. Imagine that you want to study the return property of the red part. It happened that studying the return property of the red part with respect to the full unitarian, the full Hilbert space, is like studying the return properties on the red part, on the blue part, and then combining via KHRUSHCHEV formula. Let's be more precise. Imagine, this is what I mean with this picture, but to be more precise, imagine that your unitary operator breaks in two pieces, factorizes in two parts like this, which have an overlapping at some state. Then the Schur function of the red part is a product of the Schur function of the red part with respect to the left green operator times the Schur function of the red part with respect to the blue right operator. So this means it's a divide and conquer algorithm, let's say, for studying return properties for quantum walks. If you can split in this way your unitary operator, then you can study your return properties by factorizing them in smaller pieces, factorizing the quantum walk smaller pieces. This is the way to recognize that you have this kind of factorization. This is the shape that your unitary should have. One example of this is the coin walk that I showed you in a picture before. This was the picture. Imagine that you want to study the return property of the red, the state 0 spin up, which is the red one. You can break this in two operators, and then you can apply all this machinery to study the return properties of the full system by study the return properties of the left and the right system. What about the payoffs to math? What about the phase math bridge? This is a picture you have to remember the question that I wanted to answer. Any Schur function for the real line, any Schur algorithm for the Nevalina function that appear related should be the Schur function for the real line. Any KHRUSHCHEV formula for that case. What's the trick? The trick is all what we have learned. And to understand that application tell us more than we expect. Why not use the renewable equation as a natural definition of the Schur function, both on the unit circle and on the real line? Remember, take a measure, no matter where it is supported. Define the Stilger function and use this definition of the Schur function. Sure, we know that when the measure is supported on the unit circle, this defines a true Schur function. But the surprise comes here is that when the measure is supported on the real line, this defines a Nevalina function. So this is a nice definition of the Nevalina function of a measure on the real line. It works for any measure. This gives to you new interrepresentation of Nevalina function, which were not known previously. And this also gives to do the way, but this also gives a real line version of the Schur algorithm. Remember what the Schur algorithm on the unit circle was. It was a way of producing a new Schur function starting from a previous one. So you get a sequence. And through this process, you get some parameters, and these parameters characterize your Schur function and connect your Schur function to the corresponding orthogonal polynomial on the unit circle via the recurrence relation, because these parameters are the parameters of such recurrence relation. So this connects to a ZMV matrix. I cannot explain all the details, but there is a kind of Schur algorithm for Nevalina function. They should be called Nevalina algorithms. Using again evaluation at the origin, and the parameters appearing here are nothing else but the parameters appearing in the recurrent relation of the corresponding orthogonal polynomials. The parameters, the Jacobi parameters, the parameters appearing in the Jacobi matrix. So we can characterize this Nevalina function by this sequence of parameters. This is also related to another result, which is a new representation of Schur and Nevalina function, a new operator representation, not only a new integral representation. This that appear here is the formal definition of a fair return function. You have here your operator that should be the operator of your evolution, no matter if it's a stochastic matrix of a unitary one. You have here the orthogonal projection to the orthogonal of your state. The evolution describes this operator T. This is the formula gives to you your Schur function. It happened that when your operator is unitary, the f defined by the function defined by this is a Schur function, but it also holds that when t is a Cephalion operator, you get a Nevalina function. This gives to you new operator representation of Schur and Nevalina function, which were not previously known. And what about KHRUSHCHEV formulas? Though they work here in this general setting, imagine T could be any operator, not necessarily unitary, naive, or Cephalion. What happened about, do we have any factorization? Yes, we have. This result is general and does not depend on the symmetries of your operator. Anytime your operator factorizes in this way, the return function factorizes in this way. But we have more than that, because we have also the composition rules. When you apply this factorization to a ZMV matrix, which can be done, you get the standard KHRUSHCHEV formula for the unit circle. But there are also the compositions formula. Imagine that your operator decomposes as a sum in this way. Your first return function decomposes as a sum of the left and right one. And when you apply this to a Jacobi matrix, this gives to you what you expected, a new KHRUSHCHEV formula, but this time on the real line. This is the real inverse of KHRUSHCHEV formula. And more than that, this can be done for block Jacobi matrices and block CMV matrices. This is not more difficult than to apply it to the scalar case. So you get new KHRUSHCHEV formula also, which are also valid in the matrix valid case. Kind of formula do we have? Let us remember what does the KHRUSHCHEV formula says in the case of the unit circle. You have a measure on the unit circle. You have a recurrent relation given by a SYMMETRY will depend on some parameters on the unit disk. You can define a Schur function via this formula you have there. Your Schur function is characterized via the Schur algorithm by the same parameters that appear in the SYMMETRY. And then KHRUSCHEV formula states that these modified methods have a Schur function which factorizes as a product of iterates and inverse iterates. What's happening in the real line? If you follow what I said before, what do you find? Tell the story in parallel. Imagine that you have a method on the real line. It gives to you some sequence of orthogonal polynomials on the real line whose recurrent relation is codified by Jacobi matrix, depending on two sequences of parameters. And then you can define a so-called Schur function, indeed a Nevalina function, which should be the Schur function on the real line. And when you apply the Schur algorithm, or let's say the Nevalina algorithm to this function, it turns out that your function is characterized by a sequence parameter which is the same parameter appearing in the Jacobi matrix. So, and what about the KHRUSCHEV formula? KHRUSCHEV decomposition formula tells you that the Schur or Nevalina function, let's say, of these modified methods are a sum of iterates and inverse iterates, which are defined this way. The iterates are, again, iterates. The function that you obtain after iteration of your Schur algorithm will depend on a truncation of your parameters. But the inverse iterate depend on the rest of the parameters in inverse order. Matrix version look quite similar to that one, and you don't need too much work to obtain them. KHRUSCHEV theory on the real line. I mean, the applications of all this to the real line. Can we make a classification of orthogonal polynomials on the real line using as a cornerstone KHRUSCHEV formula? This is to be done, and things are difficult mainly in the unbounded case, but there are some results. There are already some results. Imagine, for instance, that we want to characterize, as in the unit circle, as KHRUSCHEV did in the inner circle, we want to characterize when this kind of sequence of modified method is convergent. This translates into the convergence of this sum of Nevalina functions. But can we get any characterization in terms of the parameters of the recurrent relation, in terms of parameters of the Jacobi matrix? This is not so easy. This is well known in the bounded case. This was obtained by Barry Simon. And you have seen, you see here the results. Convergent modified method to the case where the odd and even sequence of the parameters A are converging and the parameters B are convergent too. What about the unbounded case? This is completely new. This is a wild situation. I cannot say that we could characterize yet all the and classify all the situation, but they are surprising. For instance, there are situations when you have convergence and do not correspond to the previous situation. For instance, Laguerre polynomials are an example of a convergent ln square. Sorry for that. Ln modulus square d mu is convergent. Sorry for that. Convergent to 0. This is one of the simple examples that does not fit with the situation on the case. And also there are wilder situation where once you know that the parameters of your Jacobi matrix have this behavior, it's possible to prove using this kind of analytical tools, this kind of Schur tools, that the corresponding modified method convert to a delta, 1/2 of a delta. And this maybe this is strange because in the bounded case, the limit measure is a probability measure always. In the two examples that I have here, the limit measure is not a probability measure, but a sub-probability one. Indeed, using this kind of Schur tool, you can go further and say something else. For instance, anytime that you have an unbounded measure such that these modified methods are convergent, you you have this situation. The limit is not only a probability measure, but it has a measure of the whole real line is no greater than 1/2. The asymptotics of this kind of modified measure is especially difficult, but especially interesting in the unbounded case. This is the interesting case. And of course, KHRUSHCHEV formulas also help you to study all these kind of phenomena in the case of metric values of orthogonal polynomials. Let's go back from math to physics once again. I don't think that the story has finished. For application of Schur function to quantum theory. No, maybe as something about the phases of matter, liquid, solid, gas, and the water. Even the ice have different phases, crystal structure, and the difference between these phases is the symmetry group behind the atomic structure. Changing a phase means changing the geometry of the atomic structure, and it is what is called a phase transition, and it means an abrupt change of properties. And discovering new phases of matter is a very interesting thing, because nowadays all other phases are known, like plasma, liquid crystal, magnet, superconductor, and you know that they have a lot of implication in technology. What I'm going to talk about, and 10 years ago, it was discovered that the materials that have different phases but with the same symmetry group. So what's the difference between two phases? It's not the symmetry group. And this was predicted theoretically in the 70s. And this prediction that was discovered to be true recently received the Nobel Prize in 2016. What is the difference between the phases in this material? They are distinguished not by geometric property, by topological invariants. They are called topological phases. And this makes you know that the topological properties are much more stable than geometric properties. Think on the winding number and the length. You push a little a curve, you move the length, but you push a little a curve, and you do move the winding number. So this physically means that you can get abnormally robust property for this kind of materials. Maybe the most impressive sample is the so-called, or maybe the most popular, is the POOL-X principle. Take two phases of this kind, topological phases, join them, no matter who you engineer this joining, and you get protected state in the interface, which means from the mathematical point of view, it means that you take two operators in two different phases, you break this operator and join them, and you get eigenvectors, stable eigenvectors. This is a result about the stability of eigenvalues, which is a more unstable, the most unstable part of the spectrum of an operator. So what happened, the picture is the following one. You have a set of operators describing possible evolution of your system, and you can connect some of them homotopical to some other, but symmetries prevent the continuous deformation of any operator into another one. So they are classified into homotopic classes. And of course, the important thing is to know the invariant, the topological invariant that classify these homotopic classes, which are the phases, the physical phases of your system. Typically, they are obtained using Fourier transform, but this is limited by you are limited by the translation to the translation invariant case in this situation. How to calculate topological invariance for the topological phases beyond the translation invariant case? Here, matrix values should finally come to a rescue, because they are something like a nonlinear version of Fourier transform. And the story continues. Don't worry, Paco. I'm going to finish with this transparency. This is all what I was talking about during all the talk. You can hear a summary of all this, but there are more things expected at the end of the tunnel. For instance, I was talking about topological phases, but you can study also recurrence. Topological phases, as I told you, are related to Schur approach to spectral theory. while you can deal with recurrent properties in open quantum walks. Open quantum walks are just quantum walks in interaction with the environment, and this needs a formalin which jumps from Hilbert space to Banach spaces. So you need Schur function on Banach space, and this we have proved that this Schur machinery also works for Banach spaces and also for open quantum walks. More problem that we smell that they have Schur function behind. The problem of occupation tames, the typical problem when you go to a casino and you want to know for how long will you be on the positive part of the I win or I don't win. This is a typical problem of occupation tames. You can formulate it for quantum walks also. And we have strong evidences that the Schur function are behind this problem also. And to finish, I just let you with all the collaborators in all this story. I just finished.
Okay, thank you very much, Luis, for your nice presentation and to put the face to your collaborators on this topic. Then we have time for questions, please. Let's go.
My question is about your formula, which you told that this is new forming polynomials on real line, which imitates Schur algorithm, yes?
Yes.
So it's like shift n to n plus 1.
Yes.
But in principle, this formula perhaps is equivalent to well-known transformation of Stieltjes function for ordinary orthogonal polynomials to associated orthogonal polynomials. This is
right.
a known transformation, yes? Perhaps
it is true.
Yeah.
It is true. This is equivalent to the Stieltjes transformation that you make by cutting your Jacobi matrix. Indeed, I think for a long time it was people thought on the Stieltjes or let's say M function as a natural counterpart, real line counterpart of the Schur function. This is in some sense it's known because it's just a translation of this algorithm to my new function. The question is that this new function opens a new way to see all relations. I don't think that you can guess easily a KHRUSHCHEV formula using Stieltjes function, but for just making this little chain, you can get something quite nice. It's the same difference that you have between Kara theory and Schur function. Nobody talk about KHRUSHCHEV formula for Kara theory functions. It's just a simple chain suggested by physics, by quantum physics, that tells you the right counterpart of the Schur function. But you are right, it's the same relation.
Okay.
But you look at it with another eyes.
Alexei, thank you very much. Another question? Great. If not, thank you again, Luis, for the presentation.